All right, good evening, everyone, and welcome. My name is Jamil Siddiqui, and tonight we're going to be doing a little bit of AP calculus problems. We're going to be looking at implicit derivatives this evening. So thank you for joining me. If you guys could just give me a hello in the chat over there so I can know that we're streaming and you can hear me all right. We're going live. Fantastic. Thank you very much. We're going to get started. So the idea of an implicit derivatives, here we go. Before we actually get to work looking at the implicit derivatives, I just want to remind everybody that you guys can follow Fiveable along on all of the social media of your choice. We give updates almost daily as to what we're covering and what the new streams will be coming out in the future. So without any further ado, let's take a look at what we're going to be looking at in this stream this evening. The first thing we're going to do is we're going to review basic derivative rules. An implicit derivative is a type of derivative. We're not going to be able to take it without knowing our basic derivative rules, so we'll start just by reviewing that. The second bullet we'll hit is what is an implicit derivative, and that goes hand in hand with why do we need them. So what's the difference between the regular derivatives we've been taking and then the idea of these implicit derivatives. And then the last thing we'll try to look at this evening is what happens when you're asked to take a higher order implicit derivative. So to start, let's just take a look at what I call the one-step derivatives. And these are the derivatives that you need to know just off the top of your head. If you commit these to memory, they're going to make your life a lot easier. And using them is going to be the kind of the starting point for all the derivatives we're looking at this evening. So I usually break them up into a couple of different groups. The first one is the derivative x raised to a number. And we all know that derivative x to the n is nx to the n minus 1. That's the first one. The next 6 I like to group together are all the 6 trigonometric derivatives. So again, you need to be familiar with the derivative sine, cosine, tangent, secant, cosecant, and cotangent. And if you know those quickly, that's going to certainly make your life a lot easier as we start looking at these implicit derivatives. The next 3 that I usually group together are what I call the derivative of the exponential functions and the logarithmic functions. So the derivative e to the x, ln of x, and a to the x. These are all what I call one-step derivatives, just problems you can answer just by looking at them. And then the last 3 that I have my students know every year are these 3 inverse trig functions, the derivative arcsine, the derivative arctangent, and the derivative arcsecant. And if time allows, we're going to look at these a little more closely tonight through the lens of the implicit derivative. But for my students, these are the 13 one-step derivatives that I really want them to be familiar with so that they'll be able to handle any of the problems that they run across on the AP exam. The next thing I want to talk about are some of the general rules of taking derivatives. Okay, those are the 13 specific functions that you should know how to take the derivative of. Now we get to what I call the general derivative rules. And the first one's kind of a common sense one. It's the derivative of one function plus another function. So if you've got f of x plus or minus g of x, the rule says that you can actually differentiate each term individually and just find the derivative of f of x and then the derivative of g of x. So this would turn into f prime of x plus g prime of x, or minus if they were being subtracted. I'm going to refer to this evening as going term by term. You can always take your derivatives going one term at a time. Okay. The next general rule of differentiation I want to talk about is just very simply, what is the derivative of a constant? So if we think about what we mean by derivative, that's slope. Well, if you graph any constant, you're going to get a horizontal line. So the derivative of constant is just going to be 0. And that's going to be true regardless of what the constant is. So derivative of a constant term by itself, that's going to be 0. So there's the second general derivative rule I want you guys to be familiar with. And the last general derivative rule I want you to know is that if you're taking the derivative function that's being multiplied by a constant, so in this case, if you've got k times f of x, when you take that derivative, what's going to happen is the k is just kind of going to get what I call a free ride to the answer, because you can pull it out and then just do the derivative of the f of x separately. And therefore, the answer you're going to get is k times the derivative of your function, or k times f prime of x. This is the derivative with a constant factor. I tend to call it the free ride rule because I like to say that k gets a free ride to the answer, and then you just take the derivative of the function that's left. So these are the general rules of differentiation that you should be familiar with, along with the one steps. The other thing that everyone should know before we get started tonight, which I assume everyone does, is the product rule, the quotient rule, and the chain rule. So just kind of verbally going over that very quickly. If you've got 2 factors that are being multiplied, you're going to make use of the product rule. A lot of people call that the derivative of the first times the second plus the derivative of the second times the first. I'm going to show you kind of a visual way of doing it this evening, but as long as you're familiar with the product rule, we'll be all set. And the same is true with the quotient rule. We're going to use the quotient rule when we've got two functions being divided by each other, and then we're going to set up the quotient rule. And then the last general derivative rule you should know is the chain rule, and that has to do when you have an outside function and an inside function. I like to say the derivative of the outside, then we copy the inside, and then multiply by the derivative of the inside. But I'm kind of taking for granted that everyone has all those under their belts already. So without any further ado, what we want to do is look at, kind of introducing this idea of an implicit derivative. But before we jump to implicit derivatives directly, what we're going to do is we're actually just going to take a look real quick at some basic derivatives to show the similarities that we're going to see between the implicit and the regular derivative. So the first example we're going to look at tonight, very straightforward. We've got a function y equals x to the fifth plus 6x squared minus sine 3x, and we are going to go and take the derivative of this equation. So I like to ask my students right away, are these those one steps? Are these the problems that we should know right away? And they look at it and they see three different things over there. It looks a little more complicated, but if you remember the term by term rule, we're going to be all set because these are added or subtracted. We can just go right down the line, do each one individually. So the first derivative we're going to take is derivative x to the fifth, and that is a one step. That's our x to the n. So when we take the derivative x to the fifth, we're going to end up with 5x to the fourth. Okay? Going to the next term, again, we're looking at 6x squared. I like to incorporate the free ride rule here, so I like to say 6 gets a free ride to the answer, and then we like to derive x squared, which again is a one step, so we're going to get 2x for the derivative of x squared. And when we go to the last term, minus 3 sine x, again, that negative 3 is a constant factor, so that's going to get a free ride. And now using our one step, the derivative of sine x is cosine x. So again, this is not an implicit derivative per se, but we need to make sure that everyone's kind of got a handle on just the basic derivative rules. So the first couple we do will be basic, and then we're going to take a look at the implicit. We simplify this a little bit, and 5x to the fourth looks good, but now we're going to do 12x and minus 3 cosine x. Now, it's the next piece of the puzzle that I really want to stress to you guys, because you probably do it without even thinking. But this is an equation when we start. We start up here and we've got this equation. We've got y equals x to the fifth plus 6x squared minus 3 sine x. What you probably don't realize is when you take a derivative, what you're really doing is taking the derivative of both sides. Okay. Now everyone sees what I just did, and everyone's happy as can be because we get those one steps over there, and that makes a lot of sense to everyone. But what people don't necessarily think about is we've got to take the derivative of the left-hand side as well. Because whenever you've got an equation, you got to do the same thing to both sides. And I've taken the derivative of the right-hand side. So now on the left-hand side, I've got to take the derivative of y. So if you got a second, if you want to put it in the chat over there, when you take the derivative of y, what is the result we're going to get? How do we write that? So I'll give you a second to kind of type that in, but the derivative of y is going to be written how? Yeah, thank you, Ronnie. That's exactly right. Okay, it's a notational thing. Leibniz created this notation, and he said that the derivative of y is dy over dx. So when I first took calculus, I just wrote that because I thought I was supposed to. I was finding the derivative. The derivative should start by saying dy over dx equals. What I never really thought about was the reason I'm taking and writing dy over dx is because I'm literally taking the derivative of y and writing that answer. So we're taking the derivative of both sides. Once I've got dy over dx, that's as simple as it gets. So it just kind of stays dy over dx, and we continue, and we get this final answer. So as we look at problems this evening, I want you to really think about that step. The derivative of y is dy over dx, and we are actually taking a derivative there. Okay, so keep that in mind. That's going to come into play later when we start looking at some of these implicit derivatives. The second example, again, kind of a straightforward problem. Y is equal to the secant of 3x squared. I just want to review another one of the derivative rules with everybody to make sure we're on the same page. So when I go to take the derivative of secant 3x squared, that doesn't look exactly like one of my one steps. Okay, the only one step I have is the derivative of secant x, and they don't look exactly alike. They've got a difference there. I've got 3x squared, whereas the one step has x. We need to pick a rule to take this derivative. So I always ask my students, is it a one step? And if they say no, the next thing we've got to do is identify, is it a product rule, a quotient rule, or a chain rule? So when you guys look at secant of 3x squared, I'm asking you for some help here. Product rule, quotient rule, or chain rule? What would you say? Okay. And thanks again, Ronnie. You're all over it. You're absolutely right. It's a chain rule. And that's because we clearly have an inside function and an outside function. The outside function, in this case, the way I write it with my students is I use those parentheses, and I just call it secant of something. And we use this word something as a placeholder. So it's the secant of something. The inside function is 3x squared. So if I want to take the derivative of this, to me, the chain rule says, start with the derivative of the outside, the derivative of secant something. Well, that's one of our one steps. The derivative of secant something is the secant of something times the tangent of something. So there's step one of the chain rule. Step two of the chain rule is to copy our inside function. Well, 3x squared is our inside function. We're going to copy it into all those something blanks we just left. So now we've got 3x squared in both of those. And then the last step of the chain rule is the derivative of the inside, and we're going to multiply. So that means now we're going to look at 3x squared, and we're going to ask, what is the derivative of that piece? Well, that's a one step. The derivative of 3x squared is going to be 6x. So I've taken the derivative of the right-hand side of the equation. Keep in mind, I still have to take the derivative of the left-hand side. So that means taking the derivative of y again. But as we said before, the derivative of y is simply written dy over dx. So our final answer here can be written dy over dx. Personally, I like to bring the 6x to the front, so equals 6x times the secant of 3x squared times the tangent of 3x squared. So again, I just want to go over this example with you guys because you need to understand the chain rule and how I'm going to work with the chain rule this evening, because that's a big part of the implicit derivative. So how are we doing so far? Is everybody okay? If you're feeling good about these derivative rules, the general derivative rules, just give me a little comment on the side, and I'll be getting ready to move on to implicit if everybody's feeling good about this. So this next problem, not really a calculus problem, okay? And great, everybody seems to be doing great. Thank you for the feedback. I appreciate that. Not really a calculus problem here. All I'm asking you to do, straight out of algebra, can you solve this equation for x? All right. So I'm just going to give you like 30, 45 seconds. I'm going to let you solve this. And if you can, you come up with the answer, just write it on the side. 40 seconds from now, I'm going to come back and we're going to go through this. So take a few moments and just try to solve this equation for x. If you have the answer, you want to put it in the chat, I would appreciate that. Yeah, as soon as you get it, you have an answer, go and throw it in there. So, okay, we're starting to get some people coming in. Great. This problem seems fairly simple, right? It's just a first degree equation. You have to solve it for x, but a lot of my students actually have a little bit of trouble. So I just want to review a couple of the steps for solving this equation. And you're going to see how the basic problems we've already looked at are going to be the lead-in problems to implicit derivatives. So with this one, we got to get x by itself. So the first step here is to choose, in my mind, which side do you want all the x's on. So I'm going to choose to put all the x's on the left-hand side. So as I do that, what I'm going to do is I'm going to subtract pi x from both sides. So if I subtract pi x from this side, I got to subtract pi x from that side. We're going to end up with 3x minus pi x plus 2 equals 7. Okay, so where do we go from here? Well, that left-hand side is the x side. We are solving for x, so we're trying to get only x's on the left-hand side. So to me, that means subtract 2 from both sides. So when we do that, we've got 3x minus pi x equals 5. Now, this is the key step right here. This is the really, really important step because we need to get x by itself, but x is actually in both terms. And it's the pi that gets people kind of a little uneasy because, if this was instead of a pi x, this has been a 10x, well, we could combine like terms and we'd be all set. But because we've got a pi, we can't combine like terms. And our job is to get a single x, and we've got 2. So I'm going to throw this out to you guys. What would be the appropriate next step to try to get that x by itself? How could I, on that left-hand side, get x alone? What do I have to do as my very next step to get x away from those 2 terms? And there we go. We're getting some great answers there, okay? That's exactly right. We're going to want to take out the GCF, the greatest common factor. So out pops the x. We got 3 minus pi, and it's equal to 5. And now from here, how do we get x alone? Well, we're just going to divide by the factor 3 minus pi. So we divide both sides by 3 minus pi, and that takes us to x is isolated, and we've got 5 over the quantity of 3 minus pi. This is the answer we're looking for, but here's the thing. You might not think that there's much of a calculus problem going on here. And to be honest, you're right. This is straight out of algebra. But what you need to understand for implicit derivatives is what we did in this step right here. In order to get that x by itself, you had to use the GCF of x. And by doing that, you went from having 2 x's to having 1 x. And that's what allowed us to solve this problem. I really want you to think about that as we start looking at some of the problems we're doing this evening. I think you're going to see kind of a common theme as we look at this, okay? So next problem, finally, let's get back to calculus. And again, we want to take the derivative here. And it's the same directions we saw in the first couple derivative problems. Find dy over dx. But there's something a little different about this problem than the first 2 derivatives we took. And if you look at it, you'll probably notice that this is not written in the form y equals. Okay? Every other problem we did, if we go back up to the top, we had y equals on the first example. In the second example, we had y equals again. So all of a sudden, I'm giving you a new example, and it's not y equals. But here's where I want you to think about what I told you before. When we take derivatives of equations. That's the bottom line. We take derivative equations. To me, this is an equation. Now, I gave this example to my class just last week, and they all instinctively, as their first step, started solving this for y. And there's nothing wrong with that. You could get y by itself very easily. You could turn this into 7 minus 3x squared over 2 equals y, and that is perfectly acceptable. Matter of fact, I'm going to kind of compare and contrast 2 ways of doing this problem. If I were to go further with this, that would mean that y equals 7 halves minus 3 halves x squared. Okay, just kind of separating into 2 separate fractions. I think everyone's really comfortable with this problem. If I asked you to find the derivative of that equation, you would say the derivative of 7 halves is 0, because that's the constant by itself. You would do a minus 3 halves gets a free ride on that, and then the derivative of x squared would be 2x. And then on the other side, you would get the derivative of y is dy over dx. So solving this for y, what you're going to find out is when we simplify this, we're going to get negative 3x as our example, okay, as our answer. But I'd like you just to think about this slightly differently. If we take derivatives of equations, don't we have an equation to start with? What would happen if we just said, let's take the derivative the way it was given to us? Would it be possible? Could we do it? Could we start with 3x squared plus 2y equals 7 and just go term by term? Well, let's try. The derivative of 3x squared, what is it? Well, that is 6x. Everybody's going to agree with that. Now, this is the one you got to be careful with. What's the derivative of 2y? Okay, well, 2 is a constant, and constant factors, we said, get a free ride. So we're going to go 2, and now all we're doing is taking the derivative of y. And I can see some of you guys in the chat. You're all over. You're right there. So the derivative of y, that's why we practiced the first 2 problems. When we took the derivative of y in this problem, we said the derivative of y was dy over dx. When we took the derivative of y in this problem, we said the derivative of y is dy over dx. Well, the beautiful thing in my mind about math is all math is the same. If the derivative of y is dy over dx, it's always going to be dy over dx. So I'm going to go ahead and I'm going to say 2 gets a free ride, and the derivative of y is dy over dx. It's exactly what we're going to get. So as we continue and we go to the other side, to take the derivative of that 7, that's a constant term by itself. Constant terms give us an answer of 0. So I want to create some language here, okay? And what I want you guys to understand is, what does it mean when we are finding? What does it mean to find? And there's a word you heard back in Algebra 1. You would always find x. Find means solve. So when I look at this problem, what I try to encourage my students to think about is, we are being given directions here. We're being told to find dy over dx. What that means to me is we have to solve for it. And to solve for dy over dx, I need an equation that has dy over dx in it. This derivative I've just taken has dy over dx in it. So all I've got to do now is get dy over dx by itself. So what are we going to do? Well, let's isolate the dy over dx. So to start with, how about we subtract 6x from both sides? And that's going to give us 2 dy over dx equals negative 6x. And then now to finish this, we're going to get the dy over dx alone. We're going to divide both sides by 2, or we're going to multiply both sides by 1/2, whatever your preference is. But if I multiply this side by 1/2, I got to multiply the other side by 1/2, and all of a sudden we're going to get that dy over dx is equal to negative 3x. And that actually, I got to admit, makes me really happy, because that's exactly what we found when we did it the first way. So one of the ideas I want you to think about right now, if you've never given this much thought before, is when we take derivatives of equations. That's what we do. As long as we take the derivative of both sides, we are following the mathematical laws we need to get the right answer. So any questions so far? If you've got anything that you want to ask, please put it over there in the chat. I'm seeing some great answers and some great comments. I'm glad you guys are enjoying this so far. But again, any questions, throw them out there. I did notice someone did ask me a question, which I'm going to answer at the end of the stream if I have time. I believe the name is Taki. I hope I pronounced that right. Asked about some tricks to memorize basic derivative formulas. At the end of the stream, I'll be happy to share that with you if you remind me. So I will get back to that. If you want some insight on how I remember those basic 1 steps, happy to share that with you at the end. So we're going to look at another example now. So in this particular equation, you might say, okay, well, my students from before said, can we get y alone? Let's start by getting y alone. You are going to have a very difficult time trying to get y by itself, okay? You're not going to be able to do it in this example very easily at all. So if you try to start this by solving it for y, you're really going to run into trouble. So let's take the approach we just talked about. Let's just say, hey, I've got an equation term by term. Can I go term by term and just take this derivative? All right. So again, I'm just going to give you maybe a minute or two to take the derivative of the left side and then take the derivative of the right side, and then I'm going to catch up with you and we're going to compare answers. All right. So just take a moment, try to take the derivative of the left-hand side and the right-hand side, if you would, please. All right, I hope you've had some time to think about this. I'm going to jump back in. We want to go through, we want to take the derivative of both sides. So in this particular example, the first term we're going to take the derivative is 3x squared y. Now, You ask, is this a one step? And it's not, because you've got an x and a y together. So now you're looking at product, quotient, or chain rule. So when you get 3x squared y, product, quotient, or chain, I hope you're thinking product rule on this one. The way I set up the product rule, okay, the way I set it up, and I'm going to be very consistent with what I always did. I always set the product rule by identifying the two factors. Okay, so my two factors are 3x squared and y. So the way I do the product rule is now I just take the derivative of each individual factor. And the derivative of 3x squared is 6x. That's easy enough. And then the derivative of y is what we've been working on all evening. It's dy over dx. So once you've got the four parts, the way you do the product rule is you assemble them with kind of a crisscross diagonal thing. So start at this bottom corner, and I assemble it by getting 6xy. And then the product rule, so I go plus, and I come back the other way. Okay, so I'm going to end up with plus 3x squared dy over dx. Whether you set up like this or not, it doesn't really matter. Just check your answer for the product rule with my answer for the product rule. We should be matching at this point in time. Okay, so now I go to the next term, which is 2x, and that's straightforward one step. So term by term, I'm going to get derivative 2x is 2. And now I go to the other side, and I want to make sure everybody's comfortable with this. And I see a lot of answers, so I'm feeling pretty good about what you guys are doing. This is a chain rule. You got to use a chain rule. Now, some people are going to say, well, why isn't it just 8y? Well, you have to remember that the one step only works when it's written like this. And I want to just point this out to everybody, okay? If I take the derivative, this right here is my notation for taking the derivative, d something over dx. If I put a 4x squared in there, I say this is a one step. And the reason I say that is because x is the independent variable in the denominator, x is the independent variable in the problem. I call that a variable match. So you can just do it as a one step. When I try to do this one, when I try to do the derivative of 4y squared, I've got problems, because x is my independent variable in my derivative that I'm taking it with respect to, but y is the variable in the problem. Those don't match. And if they don't match, you got to go chain rule. That's basically what it comes down to. If it doesn't match, it means you don't have a one step, and you got to use a chain rule instead. So now I'm taking the derivative of 4y squared. 4 is going to get a free ride because that's a constant factor. And now I'm taking the derivative of y squared. But the way I'm going to think about that is I'm going to use my inside and outside function. So the outside function is going to be something squared, and the inside function is going to be y. So when I do my chain rule, this is going to be the derivative of the outside, which is 2 times something, copy the inside, which is my y, and then take the derivative of that inside, which is dy over dx. So I saw a lot of people writing in the chat that we're going to end up with 8y dy over dx on this side, and I agree with them completely. And I also saw a lot of people coming up with the correct answer on the other side. So let's just kind of clean this up. We got 6xy plus 3x squared dy over dx plus 2 equals 8y dy over dx. So just for our terminology purposes, it is correct to say, in my opinion, I have taken the derivative of both sides of this equation. I feel like that's perfectly legitimate. I have taken the derivative of both sides. It is not correct to say I have found the derivative, though, because this word find means to solve. And we don't have it solved until we have dy over dx by itself. So now we're in a situation where I've got dy over dx is on the left side, I've got dy over dx is on the right side. I have to pick which side I want them on. Basically, I'm going to say, let's move all the dy over dx's to the right side. So this term right here has to go to the other side. So I'm going to subtract 3x squared dy over dx from both sides. Now, when I do that, what's going to happen on this side is I'm going to get 6xy plus 2. And on the other side, I'm going to get 8y dy over dx minus 3x squared dy over dx. This actually works out very nicely because now we have one side dedicated to dy over dx, one side for everything else. So here's where you're going to tell me in the chat what the next step is to get dy over dx by itself. What are we going to go back to do? And there you go. You see why we did that earlier example. Everybody's, this is fantastic. So now we're going to take that dy over dx out from that side. We're going to have 8y minus 3x squared. The common factor is dy over dx. And on the other side, we just leave it. We haven't done anything to it. So we've still got 6xy plus 2. And the final step in this is to divide both sides by, myself one more space here, divide both sides by 8y minus 3x squared. So when we do that, I'll just write it over here, dy over dx is going to be equal to, and we're going to have 6xy plus 2 in the top and 8y minus 3x squared on the bottom. This would be the final answer for this example. That would be it, okay? So that is the answer we are looking for. Any questions at all on this example? Anything you want to ask before we move on and look at a few more? One thing I want you thinking about is in all the derivatives we took previous, there were no y's. There were only x's. And now all of a sudden in these examples, we've got a mixture of y's and x's. Does anyone realize why that is the case here? What's the difference between, let's say, this example that I'm asking you guys to take the derivative of, this 3x squared y plus 2x equals 4y squared, and just going back to one of the earlier ones, this guy back here, this x to the fifth plus 6x squared minus 3 sine x. What is the difference between them structurally? Why do I need to come up with this implicit derivative? Because one of our goals for this evening was understanding why we needed implicit derivatives. So if anybody has any thoughts about that, any comments, put it out in the chat. I am going to go and do the next example, and just I want to go one more to see if anybody can kind of give me some insight on that. So in this particular example, again, it's just a little more difficult, but it's the exact same idea. We've got an equation. You are not going to be able to solve this for y. And if I can't solve it for y, I just have to take the derivative the way it looks, okay? So again, I'm just going to give you a moment, maybe a minute, and then I'll let you guys take a few seconds to see if you can come up with at least the first step. What is the derivative of both sides of this equation? And then Matt, I see your comment there. I'll be coming back to that after we take the derivative of this one, okay? So take a moment and just see if you can take the derivative of both sides here. I'll be back in about a minute. All right, let's see how you guys are doing with this one, okay? We're going to take the derivative of both sides. We're going to start with this term sine of x plus 2y. And what we got to do is ask, is it a one-step, is it a product, is it a quotient, or is it a chain? Because the x's and the y's together, it can't be one we can just do directly, so that leads us to product, quotient, or chain. And because we have an inside and an outside, I'm leaning chain rule all the way on this one. So I'm just going to kind of make a note here that the outside function is the sine of something, and the inside function is x plus 2y. And we're going to handle it from here. So when I take the derivative sine of something, we're going to get cosine of something. When I copy that inside, I'm going to copy that x plus 2y. And now this is one place where you got to be careful. Whatever the derivative of the inside is, we've got to take and multiply by what we just found. So I'm going to open up a new set of parentheses, And now I'm taking the derivative of x plus 2y. Well, the derivative of x, that's 1. X is our independent variable, so that's going to work just fine. And the derivative of 2y, well, that's going to be 2 times our dy over dx, because every time we take the derivative of y, we're going to get dy over dx. So there is the derivative of that first term. When we go to the next term, we've got x cubed y. Well, again, I'm going to set that up as a product rule the way I like to set it up. So I'm going to get the derivative of x cubed to be 3x squared. I'm going to get the derivative of y to be dy over dx. So now I'm just going to go this way and get 3x squared y plus, coming the other way, I'm going to get x cubed dy over dx. And that is taking care of the derivative of the left-hand side. So now we're going to move to the right-hand side, and that actually is a lot easier, much more straightforward. The derivative of 3x is just 3. And the derivative of 10, well, that's constant by itself, so we're going to see that go to 0. So this is what you should have gotten if you took the derivative of both sides. I see some people getting the answers, looking good. The one thing I want to just, again, stress is that I need you guys to make sure that you're using parentheses on that chain rule, because that's one place where you could get into some trouble, and I need to make sure that that you're using that chain rule. Okay, so from there, we're going to continue, because now we've got to choose a dy over dx side and an everything else side. And the problem is this dy over dx right here is kind of stuck in the middle of some factors, and we really, really need terms. So the way we're going to handle this is we're going to do exactly what the problem tells us. You've got a cosine factor times a binomial basically here. We're going to distribute. Okay, so when we do that, we're going to get the cosine of x plus 2y plus 2 times the cosine of x plus 2y times dy over dx. Okay, so I hope everyone sees that we're just making that 2 separate terms. Everything else in the problem is going to stay exactly the same. We're going to get 3x squared y plus x cubed dy over dx, and it's all going to equal 3. And now we basically just have to set up one side to be the dy over dx side and the other side to be everything else. So since all my dy over dx's are on the left-hand side, I'm going to keep them there. So you're going to see me keep that 2 cosine x plus 2y dy over dx. And that's this term right here. I'm keeping that on this side. And then I'm going to keep this on, the x cubed dy over dx on this side. And now everything else has to move to the other side. So this guy didn't have a dy over dx. This guy didn't have a dy over dx. I need to subtract them to the other side. So the 3 is over there, and you're going to see me just subtracting those other 2 terms, the cosine x plus 2y, and then the minus 3x squared y. I just want to take a moment to make sure you're really clear on this. This is the key step here, because now on the left-hand side, everybody's got a dy over dx. And if everybody has a dy over dx, that gives us our step where we can factor. So we're going to pull out the dy over dx. And when we do that, we're going to end up with 2 cosine x plus 2y plus x cubed. And on the other side, we're just going to have 3 minus cosine x plus 2y minus 3x squared y. The job here, the directions again, find dy over dx, get dy over dx by itself. So all we've got to do is divide by this factor right here. And when we do that, we're going to end up with dy over dx equals 3 minus cosine x plus 2y minus 3x squared y all over the factor we're dividing by, 2 cosine x plus 2y plus x cubed. Okay, so you can see that in these implicit derivatives, some of the answers start to get a little long, they start to get a little complicated, but that's okay, that's not a big deal. As long as we focus on our algebra, we're going to be fine. So I asked a question earlier, I asked, why do we need these implicit derivatives? What causes it? And I had an answer earlier. I believe it was Matt who gave it, and he was correct. He said, we need implicit derivatives when we can't isolate the y. If you can't get y by itself, you're forced to deal with y and x's at the same time. And to me, that's what the implicit derivative is all about. How do we handle y and x at the exact same time? So what I'd like you to think about is implicit derivatives get linked with not being able to isolate y. And that means what we're dealing with is these examples are not functions. This sine x plus 2y plus x cubed y equals 3x plus 10, that's not a function. And because it's not a function, and again, kind of just underlying information here, when we graph it, we're not going to get past the vertical line test necessarily. We could have two outputs for the same input. And that's something you're going to want to think about in the AP exam, because oftentimes when they're asking about implicit derivatives, you're going to get problems where you get two outputs for the same input, and that's going to work a little differently than all the functions. So I'm going to try to show you an example of that in just a few minutes, but I just want to kind of put that in the back of your mind right now. So let's look at one more example here. This one's very similar, except for you might notice in our Leibniz notation, it's not dy over dx. All of a sudden, in this problem, we're actually being asked for d squared y over dx squared, which I hope you all recognize just means finding the second derivative, okay? So what I'd like you to do is I'd like you to take a minute, again, go through, let's find the first derivative. We'll check the first derivative with each other in just a second, and then we'll talk about how do we handle the second derivative together. So I'll just give you a minute to come up with the first derivative. I'm going to start working on myself while you guys are doing. We'll compare our answer in a second. Okay, so my first derivative, when I went through it, I got 2y dy over dx. And again, I was using the chain rule to differentiate the y squared. Then I did a product rule to do negative 2xy, and I got negative 2y minus 2x dy over dx. And then on the other side, derivative 6x squared, I got 12x. So I see some people agreeing with me, so I'm feeling pretty confident about this. Now, again, our job is to isolate the dy over dx. All my dy over dx's, I'm just going to move this over. All my dy over dx's are on this left-hand side. So I'm going to keep that where they are. So I'm going to get 2y dy over dx. And then I'm going to get minus 2x dy over dx equals 12x on the other side. And then I'm just going to take a moment and add this 2y to the other side. So I'm going to get 12x plus 2y. All right. So hopefully everyone's feeling good about this. We're going to factor out that dy over dx, which again is the key step here. And that's going to give us 12x plus 2y. And now we're going to divide both sides by the 2y minus 2x. And as we do this, we'll probably factor out a 2 from the top and the bottom. And we'll end up with 6x plus y on the top. We'll end up with 2 times y minus x on the bottom. And that will simplify to 6x plus y over y minus x. Okay, so I hope everyone's feeling good about this. And now we've got the first derivative. Well, this question actually asked us to go further. It said, don't stop at the first derivative. Now we want to find the second derivative. So I'm going to give myself some space over here. And we've got to start from here and take the derivative again. Okay. But the good news is we've got an equation and we can take the derivative of both sides of equations. Just got a question about, do we have to simplify our answer in the end? Okay. So this is a tricky question. Let me explain why. It all depends on what your purpose is. If all I'm doing is asking you to find the derivative, and I'm testing you on your derivative skills, and this is my personal feeling as a teacher, I don't mind this answer right here. That answer shows me you took the derivative correctly. But if you're taking a test and it's an AP exam and you're trying to find your answer as a multiple choice question, you're not going to see this answer as one of the multiple choice questions. You're going to see the simplified version. So you're going to have to simplify it. So this is what I tell my students. I'm like, you should know how to simplify it. You should be prepared to simplify it. But if the question is just trying to prove to me you know how to take a derivative, then it's not necessarily needed. Okay. My best advice to you guys, though, is to always check with your own teachers and to make sure you know what they're looking for. Even if you don't have to simplify it, you should know how to simplify it. So that being said, I want to go ahead and I want to now go and look at dy over dx equals 6x plus y over y minus x. And I've got to take the derivative of this. I've got to find the second derivative. So if you guys don't mind, I'm going to take this and I'm just going to write it up here real quick. And I'm going to write all my work in the next column. When I go to take this derivative, the derivative of the left-hand side works exactly the way I want. It's going to be d squared y over dx squared, because that's how you write the derivative of the derivative. And then I see Robert already mentioning, hey, on the right-hand side, we got to go quotient rule. There's no question about it. So again, the way I set the quotient rule, and just give myself a little more space here. The way I set the quotient rule, what I want to do is I want to make use of my boxes again, just to organize it. So I'm going to put 6x plus y in this box. I'm going to put y minus x in the box next to it. And then I'm going to take the derivative of each of these terms. So the derivative of 6x is 6. The derivative of y is dy over dx. We don't forget about the dy over dx. We still need it. It's still the derivative of y. So every time we take derivative of y, it's dy over dx. In these next terms, the derivative of y again is dy over dx, and the derivative of negative x is negative 1. So the way I set up the quotient rule is I always remember to take my original denominator and square it. So that's the first thing I do. And now I actually do this crisscross idea again. So it's going to be 6 plus dy over dx times y minus x. And then because it's the quotient rule, I get a minus. And now I'm going to go the other way, and I'm going to get 6x plus y. And it's going to be times dy over dx minus 1. I hope everyone can read that okay. Okay? So I have correctly taken this derivative. But here's the problem. I don't have an acceptable answer. Okay? When you take an implicit second derivative, you can't leave dy over dx in your answer. And that's what's going on here. So my left-hand side, perfect. D squared y over dx squared. My right-hand side, I can't have those dy over dx's. So if you got a second, how do I get rid of them? What's the way I'm going to get rid of those dy over dx's? Because I'm not allowed to have them in my final answer. And the way we do it is we go back to where this first derivative started. We know what dy over dx is equal to. You guys are answering it now, so that's great. So the way I'm going to answer this question is I'm going to do 6 plus, and I'm going to go back and use our original dy over dx from the top of the page. So that's 6 plus dy over dx. Y minus x is perfectly okay. Minus 6x plus y. And now I've got dy over dx minus 1. I apologize. I'm running out of room. I'm going to squeeze it in. So I'm just going to write it down below. But I'm not going to use dy over dx. Literally, I'm going to plug in for it again. And I'm going to get 6x plus y over y minus x. And then minus 1 there. Don't forget the minus 1. Minus 1. And that entire expression is the numerator of my answer. What do I still have? I still have that denominator floating around. So it's all going to go over y minus x quantity squared. So what I'd like to do is I'd like to write this the way I would expect my students to write this, okay? The way I would have my students write it is I would have them say, starting over here, the second derivative is equal to 6 plus 6x plus y over y minus x. There's my first factor. Y minus x is my next factor. Minus 6x plus y is the next factor. 6x plus y over y minus x minus 1 is the next factor. And now, because this all has a denominator, I prefer to write it off to the side as 1 over y minus x quantity squared. Okay, so these second derivatives can get extremely long and complicated, but the fact of the matter is, as long as you have all the pieces, what I have written right here would earn you the credit point for taking the derivative correctly. This would earn you the point. Most of the time, they're going to have a follow-up question and have you plug in some values, but this is going to earn the point, and you're going to get credit for this answer. So I hope that makes sense. What I want to stress on this problem again is every time you do a second derivative with an implicit, every single time, you're going to use your first derivative to replace it, okay? So here's my second derivative. You're going to notice a first derivative in the answer every time. You're going to use the answer to your first derivative to replace that dy over dx every single time. So I hope that makes sense to everybody. Probably going to have time to do one more question here, so I want to look at this one. This is a find the equation of a line tangent question. Very, very popular question on the AP exam, okay? And I'm going to work this out with you. We're going to do it together. The place I like to start this question is right here with these words, find the equation of a line, okay? Every single time I find the equation of a line, this is what I write down. And that is the equivalent of the point slope form, okay? All I have to do is fill in these three blanks. You fill in these three blanks, you're home free. So as I'm looking, if you guys remember, this blank right here is for a y value, this blank right here is for a slope, and this blank right here is for an x value. And the x and the y value have to come from the same point. So now I'm looking and I'm asking, is there any value that I can use that I know? And you know, if you can read, they're making it pretty clear. They want us to use y equals 2. So how about we take that 2 and we plug it in there for the y? But the problem is I need a point, and that's just telling me the y value. I still need the x value. So where am I going to get the x value from? Well, this is where the original equation comes into play. This original equation right here tells me the relationship between the x's and the y's. So I know the y value is 2. Using this, I can find what the x value is going to be. So I'm going to take that 2 and plug it in. And when I do that, I'm going to get x squared plus 6x plus, and this is where it's kind of tricky because we're so used to plugging in x all the time. In this question, we're actually plugging in y. So I'm going to put in a 2 for that y. Instead of y cubed, I'm going to get 2 cubed, which is 8, plus 2y. But again, I'm plugging in 2 for the y, so I'm going to get 4. And then on the other side, I've got equals 3. So as I look at this, I've got x squared plus 6x plus 12 equals 3. Well, this is a degree 2. So I'm going to move everything the same side. I'm going to get x squared plus 6x plus 9 equals 0. I'm going to factor this to solve it. And I'm going to get x plus 3 times x plus 3, which means my only solution is x equals negative 3. So now I know that the x value at this point has to be negative 3. Go back to my point slope form. I'm going to plug a negative 3 into the x value. But by doing a negative 3, it's actually going to change that sign to make it a positive 3. So I hope everyone's following this and is okay with what we've done so far. Because to be honest, we haven't done any calculus left. This is all just equation line work. So the only thing left to do to fill in this equation line is to find our slope. And how do we find the slope? Well, in calculus, the way we find slope is always the same. We take the derivative. So Here's your last chance to do a practice problem this evening. I'm going to give you guys a second. Would you please take the derivative of x squared plus 6x plus y cubed plus 2y equals 3? We'll check our answers in just a second. So I've gone through and I've taken my derivative of the equation. I see a lot of you guys are doing the same thing. We seem to have a lot of matching. So once we've taken the derivative of both sides, pick a side for dy over dx. Everybody else goes on the other side. So how about we keep this left-hand side, the dy over dx side. And we're going to move minus 2x on the other side, minus 6 on the other side. And then from there, again, the key to this, all the dy over dx's are on one side, so that allows us to be able to factor them out. So we get 3y squared plus 2 dy over dx equals negative 2x minus 6. And now we're just going to divide both sides by our 3y squared plus 2 factor, and we're going to end up with dy over dx equals negative 2x minus 6 over 3y squared plus 2. Hope that makes sense for everybody so far. The question that we need is to find the slope, but the slope is at a specific point. So we want to take this derivative and we want to evaluate it when x is equal to negative 3 and when y is equal to positive 2. So what we've got to do for this is plug in the x value of negative 3. So it's going to be negative 2 times negative 3 minus 6 on the top. And then on the bottom, we're going to go and we're going to put in 2 for the y. So it's going to be 3 times 2 squared plus 2. When we compute this, what we're going to end up with is 0 on the top. And if we do the bottom out, we're going to get, what, 4, 12, 14 on the bottom. But the bottom line is the slope is equal to 0. So once we know the slope is 0, we come back to the original equation. We put 0 in. And to be honest with you, you would be perfectly okay leaving this answer exactly like that. That answer is 100% correct. Most people are going to want to see that simplified a little bit because the right side has a factor of 0. What we really end up with from here, I'm just going to write it down here, is that y minus 2 equals 0. Or in other words, we're going to get that y equals positive 2. But both this answer, y equals 2, and our point slope version would earn full credit on this. So you guys could leave either answer and be perfectly okay. Any questions on anything we've done this evening? If you have any questions, you have any comments, please put them up in the chat. I'll be happy to answer any questions. There was a question from earlier that I just want to talk about really quickly with our remaining time. Someone asked me, is there an easy way to remember the derivatives? Okay, those one-step derivatives. I'm going to show you how I have my students remember the trigonometric derivatives. Okay, I'm going to show you how this works. So derivative of the 6 trigonometric functions is what I'm writing down right now. Derivative of cosecant and the derivative of cotangent. Okay, so these are the 6 trig derivatives, all right? And the way I remember them is the following. Whenever you hear sine, to me, the first thing you think of, the first trigonometric function you think of after sine is always the same, it's cosine. So most people do not have a hard time just remembering the derivative of sine is cosine. That's usually a pretty straightforward one, okay? So assuming you can remember that one. Well, if the derivative of sine is cosine, it would be nice if the derivative of cosine were sine. but it doesn't quite work that way. So I'm going to tell you two little stories real quick that I use to help me remember them, okay? So the first story is that when I was in school, my mom made a deal with me, and she said, as long as you get A's and B's in class, you're going to be fine. We're never going to have any problems. We're going to get along great. And of course, I want to make my mom happy, so I was like, all right, we'll do that. But because of that, I got this idea that a C was not a good grade. It was negative. It was a bad experience. So if I got a C, my mom would be unhappy, and then I'd be in some trouble. So I always remembered that this idea of C made me think of a negative connotation. Little did I know, my mom was just helping me get ready for calculus, because what I learned was that if you're taking the derivative of a trig function that begins with C, the answer is automatically negative. So right away, I'm putting in those three negatives, okay? So I know those three have to be negative. So now, when I say derivative of sine is cosine, everyone can remember that. What's the derivative of cosine? Well, we want to say sine, but we remember that we need to have a negative with it. So we've got the first two. The derivative of sine is cosine. The derivative of cosine is negative sine, okay? So from there, where do we go next? Well, this is the key one, remembering this tangent one, okay? So if we want to remember this tangent one, this is what I need you to remember. And I'm going to set up a little visual, because this is what always helps me remember it, okay? 3 blanks to fill in, and here are the 3 things you're going to fill in the blanks with. So here's what you have to remember. There are 2 secants to 1 tangent. If you can remember that ratio, 2 secants to 1 tangent, you're going to be home free. Because if you remember there are 2 secants to 1 tangent, when you go to fill in your blanks, the derivative of tangent has to be the 2 secants that are left over. So that gives you what you need. You get the derivative of tangent equals secant squared. So again, this is kind of the important one. You need to remember this one, okay? 2 secants to 1 tangent. Because now, if you've got that, let's reset everything. Oh, and you remember 2 secants to 1 tangent. Well, now if I go to the next one, I want to know the derivative of the secant. Okay. The derivative of the secant goes here, and then what's left for your 2 blanks? Secant times tangent. So all of a sudden, you've now got a way of remembering what the derivative of secant is. And it's this ratio, 2 secants to 1 tangent. So now the derivative of secant is secant x tangent x. Okay, and it's all about 2 secants to 1 tangent. So now, how do I take this one step further? How do you make sure you remember the derivative of the other 2 trig functions? Okay, well, here's the deal on this one. We've got an equation. Right up here, we've got an equation. And I can do whatever I want to the equation as long as I do the same thing to both sides. So this is a little silly, but it works for my students, and they seem to remember it pretty well. Here's what I tell my students. You've got the derivative of secant, but we want the derivative of cosecant. So I can do anything I want as long as I do the same thing at both sides. So this is what I do. I say, okay, everybody, write co in front of everything on both sides. And if you do that, the derivative of cosecant looks like cosecant cotangent. However, you know it's got to be negative. So all you're doing is saying co in front of everything of the secant derivative, okay? And just remembering that the answer is negative. So if you've got this down, then your last one is the derivative of cotangent, but hopefully you can see what's going to happen here. The derivative of cotangent is the exact same thing as the derivative of tangent, except for you've got to put co in front of everything. So instead of tangent's derivative being secant squared, cotangent's derivative is cosecant squared, and because it begins with C, you've got the negative. Okay, so that's kind of the rules that I use. That's my mnemonic, my way of remembering it. I quiz my students with it every year. They seem to do pretty well with it. I hope that makes sense for you. We are just about out of time here, so any last comments, feel free to put in. If you guys don't mind, if this was worthwhile, if you guys got a good handle on the implicit derivative by watching this evening, please give me some feedback over in the chat session. And if you have any requests for topics you'd like to see in the near future, please put it over in the chat, okay? So feedback and topics that are coming up, please let me know over there in the chat section, and we'll be sure to work that in. Thank you for joining us this evening. Be sure to follow us on our social media. And tomorrow, if you want to come back for more, we're actually going to be streaming the same time. And Stephen, you've got it. We're going to be doing related rates tomorrow night, 9 o'clock p.m. Eastern Time. So if you want a review on related rates, please join us tomorrow night at 9 o'clock. We'll be right back here. Okay? Thank you all for coming. I appreciate it. Hopefully we'll see everybody tomorrow night. All right? Have a great evening. Tomorrow night, related rates, 9 p.m. All right. Thanks for your time this evening. Enjoy the rest of your night, and good luck.